Another similar triangles question, well, at least it starts off that way, it progresses loads. In addition to the circle theorems when we did it earlier in the paper. Now this is one of those most difficult types of questions. It's a show that question, which means we're going to have to communicate our maths very well, which helps being neat and saying things out, which is not easy for me on this iPad with this terrible size. But we'll give it a go. Now, in order for triangles to be similar, the three angles need to be the same. So we need to prove they're the same. The easiest ones to do straight away is this. This angle here, which is terribly coloured in, is got to be the same as that angle there. Okay, and I'm going to do. The way I'm going to write that is that angle MON is the same as POQ. And I'm going to write down a reason for that as well, which is that opposite angles are equal. Okay, on to our next ones, and the trick here is that we've got parallel lines, so we've got some alternate angles, or Z angles. This one here is the same as this one here, and if you can't see that, try rotating your piece of paper or your iPad you're watching this on. That's a Z angle. Two parallel lines there and there, line in between them, cutting them there, so they are equal. I'm going to write that on. I'm going to call them NMO, and MO with my little hab of the M, and that's the same as PQO, and that's our angle in the bottom right, and they are the same because they are alternate angles. Finally, we've got another pair which is exactly the same as last time. Hopefully you'll be able to see it now. I'll run over it quickly with my little pointer. This is another Z. It's a sort of upside down Z. Put it the other way around, however you want to think about it. It's still alternate angles. So that is MNO and QPO. They are the same as each other. So now we've shown we have three equal angles, and so they are similar. Just for belt and braces, I've written over here that statement, three equal angles, therefore they're similar. Now I've got to point out these three explanations are absolutely crucial. If you just say there are three equal angles, so therefore they're similar, that's not good enough. We've got to show they're similar, show why are those angles equal. You can't just sort of measure them or pretend they are. We've got to give some basis behind it all. Okay, so on to part two of that, which is again using our using the fact they're similar. It tells us some information here. We can already tell from above. So we've now got to explain this. Well, there's a couple of ways of doing it, but possibly the easiest is to say the ratios need to be the same. And if the ratios in the triangle are the same, we're gonna end up with a few different rules. So because they're equal, I'm going to write it. I'll pause it and write it now. Actually, so similar triangles have the same ratio between sides. So what that means in our context here is the ratio 4:5 has to be the same as the ratio 2y minus 2, y plus 1. So writing that down, the ratio. So that's what I get when I divide them. Right. Okay, there we go. So that's what I get when I think about them being the same ratio. 4/5 is the same as y plus 1 over 2y minus 2. Now, it's not the same as what we got, so the final step is to just say, if I then multiply both sides by, 2y minus 2, and divide both sides by 4, I'm going to get that. And it's shown. Now there are loads of different ways of showing or explaining that, but generally speaking, it's the ratios of the sides that are the key part. Right now we're asked to solve this equation, which we were just messing about with. So I'm going to write it again to start us off. 2y subtract 2 over 5 is y plus 1 over 4. So I'm going to do some cross multiplication. I'm going to multiply by 4 and by 5, essentially multiplying by 20. that gives me 8y subtract 8 is 5y plus 1. Oops, classic mistake there. That should be 5y multiplied by 5y plus 5. So now subtracting 5y from both sides gets me 3y on this side, and adding 8 to both sides gets me 13 over there. So I get y equals 13 over 3. Now I could do all sorts of that, putting it as a recurring decimal or a mixed number, but I'm not going to. Right, now we know what y is, we can solve all other sorts of bits. For example, the length of NP. So just traipse all the way back up to the top here. NP is this length here from one corner to the other, so it's a 4 centimetre, then a y plus 1. 4 centimetres plus a y plus a 1. There we go, so I can substitute what I know y is into there and combine the other terms. So NP is actually 5 plus 13 over 3. Well, 5 is going to be 15 over 3, so that means I'll get 28 over 3 as my solution. Again, you could write it as a mixed number, which is 8, 9 and a third, but you could write it all sorts of other ways. Now, this next question is not the sort of question that would come up anymore. It's from a 2001 paper. Your calculators just tell you the answer now, which is nice. You should try and remember them. There's a nice little thing with a hand which is useful to remember them, but we'll just say, there we go, it's a half bonus, 1 mark for free, essentially, by being able to plug it into your calculator. Okay, so this bit wants me to refer back now to part B. So using my answer to part B, which is sine B equals a half. Now, how does that help us? Well, sine, hopefully you remember, is not just some random 3 letters. It's equal to the opposite divided by the hypotenuse in a right-angled triangle. So if it's sine of 30 degrees in this instance, which we have here, sine of 30 is going to be the opposite over the hypotenuse. So I'm just going to write that down. So what we're saying is sine 30, just looking at this triangle, is a half, we know that, but it's also, in this triangle, the opposite over the hypotenuse. So that would be x minus 3 all squared over 30 minus 4x. So I've got myself an equation there. I can choose to just sort of ignore everything on this side and go with my half equals to that. So we've got an equation x. That's part of the question done. Now we've got to hope, well, maybe I've got it wrong, but I should find out. If we manipulate it round, we should get what it put here. Hopefully we've done all the unusual part there. So I'm going to do my standard cross multiplying, where I take that, multiply that by that, and that by that. So I will get 30 minus 4x on the left is equal to 2 lots of x minus 3 all squared. Just to help me in a second, I'm going to write that as that because I'm just about to multiply it out. Common mistake with 30, with x squaring x minus 3 is just to do x squared minus 3 squared. Absolutely rubbish if you do that. Right, so I've got 4 multiplications. X times x is x squared, x times 3 is that, x times negative 3 is that, negative 3 times negative 3 is that. Double them all as well, and then we should just be able to rearrange to make it equal to 0. Fingers crossed we'll have the same answer. So that would have been negative 6x, but I'll double it to make it negative 12x, and then the positive 9 I'll double to make 18. So it's not exactly looking great at the moment if I just glance up at what I've got, because up here I've got just an x squared, not a 2x squared. I've got a negative 6, not an 80. But we can see everything here is a multiple of 2. So before I do anything else, I'm just going to divide everything here by 2. 15 minus 2x. Smaller numbers are nicer to deal with as well. Minus 6x plus 8 plus 9. So simplify that down. I'll keep my x squared. I'm adding 2x to both sides, so it's negative 4x, and then I'm subtracting 15 from both sides. That should be a better plus. So I get negative 6. Oh, look, it's worked. Well done. That was a very long paper if you managed to complete it, and some very long video solutions here. I hope they've helped though. And as a reward, if you've got here, here's a joke. How do cows subtract? They use a calculator.